Okay, moving on then to number 10. A cross-country running course is given in this diagram. We have to show that the distance CA is 943 meters. So show that. So let's ignore the answer. We're not going to use it in our solution. Well, we're lucky because we've got a right triangle, and two of the sides in that right triangle have been given. So when we have a right triangle, we know that we can use either Pythagoras or SOHCAHTOA. In this case, we'll use Pythagoras. So 500 squared plus 800 squared equals x squared. And so, let's see, 500 squared plus 800 squared equals big number. 890,000 is x squared, and let's take the square root of both sides then. Square root of 890,000 equals 943. Now this is where, so I'm actually going to write this out for a moment, because it's a show that question, and when you see a show that question, please write every single possible step. It's where you want to be the anti-Calvin. X is the square root of 890,000, and, 890,000, and we'll take the square root then of, and we got approximately 943 point, and I'm going to write the unrounded answer first, or at least a few digits of it, and then I can say, okay, well look, I can round this to 943 meters, and reveal the answer, and hey presto, look, I got the same thing, 943 meters. Okay, but don't write down 943 meters anywhere in your process until you arrive at it yourself. And when it's a show that question, two things to remember: write every single step in slow motion, and secondly, write down the unrounded value before your final answer, which should correspond to the show that. Okay, part B. Show that angle BCA is 58 degrees. So let's just clear a little bit of space here. BCA, we're looking for this one here. Well, that's no problem, because in a right-angled triangle, I know I can use SOHCAHTOA in order to find angles. And so relative to this angle, I've got the opposite side, which is 800, and I've got the adjacent side, which is 500. I know I just solved for the hypotenuse, so I suppose I could use a sine or a cosine ratio, but why use the hypotenuse whose length is not exactly 943? The opposite and the adjacent are exactly 800 and 500, so why don't I use then the tangent ratio so I can be dealing with as exact values as I can? And so this means that theta is going to equal then the tangent inverse. Look, the hundreds cancel out, so it's just 8 over 5. And so the tangent inverse of 8 over 5 gives us 57.9946 degrees, which of course we can round to three significant figures. That's 58.0 degrees. Don't forget your degrees sign. Oh gosh, I didn't really pay very careful attention. I've done exactly what I was supposed to do. I completely ignored the 58.0 degree measure in my process, and independently I showed that by writing down every single step, my original trig ratio, and then my isolated angle, and then my unrounded answer, and then my rounded answer, correct to three significant figures. Okay, so good job me. Part C, part I. Calculate the angle CAO. So I'm looking for this one here. Okay, well, I suppose now that I know that this angle is 58.0, I should be able to figure out what, let's not call it x, I should be able to figure out what this angle down here is. Let's call it alpha. Because the sum of the three angles in the triangle is 180 degrees, so 180 degrees minus 90 minus 58 will give us alpha. Let's see what we get. 180 degrees minus 90 minus 58.0 degrees should leave us with the remaining angle measure of the triangle ABC. So 180 minus 90 minus 58, and we're left with 32 degrees. So if this is 32 degrees, and then this entire thing was 110 degrees, so here's 32, the whole thing is 110, well that must mean that this amount is the difference between them, right? And so we'll go 110 minus 32, and that gives us 78 as our answer for angle CAO. It's 78 degrees. Part double I, calculate the distance CO. Okay, so let's just erase some of this extra work. And so this right here I now know is 78 degrees. Right, alright. And, oh, I also know the value of x, don't I? I found this earlier on. It was about 943. Alright, calculate the distance CO. Let's call this this guy y. Now in triangle CAO, if I examine this entire triangle, because every time I see a triangle I have to think about it as a triangle, is it a 90-degree triangle? I have no evidence to support this. I've got a 78-degree angle, but I don't know what this is, I don't know what this is. So I don't know if it's a right triangle. It probably isn't. But I certainly can't assume that it is if I haven't been given evidence to support that. So let's assume it's not a right triangle, in which case I have to use the law of sines or the law of cosines. I should use the law of sines if I have an opposite pair. I don't have the angle opposite 943. I don't have the angle opposite 1500. I don't have the side opposite 78 degrees. And so I'm going to have to use the cosine law. And because I'm looking for a side, let's use the first cosine law that's in the formula booklet. The one that starts with the y squared. So y squared is going to equal the other two sides squared, 943 and 1500, minus 2 times the product of those two numbers times the cosine of the angle in between them. And then in order to find out what y is, I'm going to find the square root of all of that stuff. So here we go, the square root of 943 squared plus 1500 squared minus 2 times 943 times 1500 times the cosine of 78 degrees. Gives me an answer of 1,597, or if I rounded to 3 significant figures, it would be 1,600. I tell you what, I'm just going to write down 1,597 meters. I think it's good enough to the nearest meter. So that's my distance CO, 1597. Alright, let's move on then and look at the... just a sec while I find my place again. Okay, so yeah, let's find now the area of the triangle. In fact, I have to find the entire course's area, don't I? So I guess the entire course's area will be this bottom triangle plus this top triangle. Now, we have to treat these two triangles in different... Well, we don't have to, but we should. Let's treat these two triangles in different ways. Oops, sorry. There we go. This bottom triangle, I've already got a right angle in it. And so this is a very simple area formula to use. I'll just say 1/2 times the base times the height. This one up here, however, I don't have a base that is perpendicular to a height. I don't have any perpendicular altitude information about it. It's not a right triangle. But I do have two sides and the angle in between them, so I can use the alternative area for the triangle formula. So we're going to add then these two triangle area formulas together in order to calculate the area of the entire course OABC. Why don't we start with the bottom one then? 1/2 times base 800 times height 500. So here we go then. The total area is the bottom one, 1/2 times 800 times 500. And then we've got the upper triangle, whose formula is 1/2 times AB. Let's see, what were those lengths? We know this one was 943, and the one on the right is 1500. Okay, 1500. And so I always multiply two sides times the cosine of the angle, excuse me, I'm wrong, times the sine of the angle in between them. Sorry, when we're dealing with an area, we work with the sine of the angle in between. It's when we're dealing with the cosine law that we work with the angle in between. Okay, so let's add this stuff up. We've got 0.5 times 800 times 500 plus 0.5 times 943 times 1500 times the sine of 78 degrees. And wow, that is a pretty big area, 891,000. In fact, if I rounded to three significant figures, I would get an area of 892,000. And we're dealing with meters squared because it's an area. Okay, Gonzalez runs at a speed of 4 meters per second. Okay, as soon as they've given us velocity, speed, you've got to be thinking velocity is distance over time. Write it down. Calculate the time in minutes taken for him to complete the course. So they're looking for us to find the time. Time, if we rearrange the formula, is equal to distance divided by velocity. You can see earlier in a previous video why this is. So let's substitute then. We need to first find the overall distance, and the overall distance is going to be the sum of the distances around the course. That's 500 plus 800 plus 1500 plus the y value that we found a little bit earlier on this problem, which was 1597. So let's add up those four values. So 500, 800, 1500, and 1597. That's the total distance he ran. And we need to divide this by his velocity, which is 4 meters per second. So this was the total in meters. The meters are going to cancel, and we'll be left with seconds. We're going to have to change that into minutes in a minute, so do watch out. Alright, so 500 plus 800 plus 1500 plus 1597. And that total, let's divide it by 4. So the total amount of seconds is about 1099 seconds. Let's divide this then by 60 in order to find out how many minutes this is. And if I round to three significant figures, I'm going to get approximately 18.3 minutes. And we've done, finally, number 10. Let's move on to number 11. Oh good, a shorter question. Boy, we've done several problems like this already, haven't we? We're looking at a triangle. Is it a right triangle? Should be the first question that we ask ourselves. We have no evidence to show us this is a right triangle, so we cannot use SOHCAHTOA nor Pythagoras. Can we find an opposite pair? No, we cannot, so we cannot use the sine law. The only strategy left available to us is the cosine law. We're looking for the length of a side, and so let's use the first cosine law. I'm going to call it x, so x squared. Here's Pythagoras, 3.9 squared plus 4.8 squared as the beginning of the cosine rule formula, but then I need to subtract 2 of these in order to correct for the fact that it actually isn't a right triangle, and we've got the cosine of the angle between, cosine of 82 degrees. X is going to equal the square root of all of this stuff. Let's see what all of that stuff gives us. 3.9 squared plus 4.8 squared minus 2 times 3.9 times 4.8 times the cosine of the angle in between. Okay, so we're going to be taking the square root of this number, 33.03936, if I round to more significant figures than I need. So the square root of the answer I just had is equal to 5.75. So the length of AC is about 5.75, and my units is centimeters. Okay, 5.75. Now let's calculate the size of angle ACB. ACB, that's this guy, okay? So I'm always looking at the middle one, C, angle C. Well, I didn't have an opposite pair before, but now I do, because I now know the value of x. I've discovered that it's approximately 5.75. So now that I've got an opposite pair, I can use the sine rule. So the sine of 82 degrees over 5.75 is equal to the sine of the angle I'm trying to find, let's call it C for short, over its opposite pair, 3.9. Let's cross multiply and then divide both sides by 5.75 to get the sine of C alone. So in order to get C alone, I'm going to need to take the sine inverse. Move the sine across, it becomes the sine inverse of all this stuff. 3.9 sine of 82 degrees divided by 5.75. Now 5.75 is actually an approximate amount, so I'm going to be able to call it my answer of the exact amount. Here we go. The sine inverse of 3.9 sine of 82 divided by, so notice how I closed the brackets on the 82, divided by my answer from before, which is a more accurate version of 5.75. And I get 42.2, and of course this is in degrees, 42.2 degrees. Number 12. So I've got an office tower which is in the shape of a cuboid on top of a rectangular pyramid, prism, sorry, they call it a cuboid, with a square base. So let's calculate to three significant figures the size of the angle between OF, and we've been told that all of these, well, we haven't been told this, but look, if this length is 10 meters, that must mean that this length right here, and this length right here, and this dotted one here at the back, all of these have got to be 10 meters because they all represent symmetrically the same distance from the apex of the pyramid to the corner of the square base. So these are all 10 meter lengths, 10 meters. We also know that if it's got a square base, that not only is this length 6, but this length must be 6, thus this length must be 6. So let's find now then the angle between OF and FG, this angle right here. Well, I've got a couple of methods available. One method I could use is, because this is an isosceles triangle, I could drop a slant height down that will split my 6 meters into two 3 meter sections, which are each parts of right triangles. Now this only works because it was an isosceles triangle. So that's a nice way of doing it. If we can form a right triangle, then the problem becomes a lot easier. So this angle then would simply be, so the cosine of that angle, isn't it? It's adjacent. So the cosine of our angle is adjacent over hypotenuse, and so theta will equal the cosine inverse of 3/10, and the cosine inverse of 3/10 is equal to 72.5. And so I've got my angle. But I'll show you another way you could have done it. If you didn't think about dropping this perpendicular down, then another way you could have done it is by observing this whole big triangle, OGF. And so we're now dealing with three sides. We know that we've got 10 meters, 10 meters, and 6 meters. And we don't have an opposite pair. This big triangle OFG, we've got no evidence it's a right triangle, so we'll have to use the cosine law. And because we're looking for an angle, let's use the second cosine law. So the cosine of the angle will equal the squares of these sides on each side of the angle I'm trying to find, that's 10 squared plus 6 squared, minus the square of the opposite side. Right? We always subtract the square of the opposite, minus 2 times the original 2. Alright, so theta is going to equal the cosine inverse of all of this stuff, 100 plus 36 minus 100. Oh look, the 100s cancel, that's interesting. Over 2 times 10 is 20 times 6 is 120. So we're left then with the cosine inverse of 36 over 120. And lo and behold, that gives us the exact same answer, 72.5 degrees. So it doesn't matter whether you drew your slant height and used two right triangles, or whether you didn't draw your slant height and used the cosine rule, you still end up with an answer of approximately 72.5 degrees. My preferred solution would probably be this one, the one where we did draw the slant height, because I bet you that later on in this question we're going to need it. Every time we see a pyramid, I can almost guarantee you that at some point you're going to need to draw the slant height and do some stuff with Pythagoras there. So let's see, the shortest distance from O to FG. Oh, there we go. The shortest distance from O to FG is, of course, going to be this very length here. Okay, because that's going to be shorter than going sort of like, let me draw that triangle kind of straight up for you. Imagine any triangle, and this is our O at the top, and this is the F, and this is the G. So what's the shortest distance to the line? Well, I could go the long way, but I mean, if you were swimming to shore, wouldn't you just head straight for shore? And that's going to be the slant height, isn't it? And so this distance we can find from the right triangles that we were working with a moment ago, where we'd split the 6-meter measure into two 3-meter measures. And so this length here, if I call it x, I can use Pythagoras, can't I? Because it's a right triangle. X squared plus 3 squared equals 10 squared. X squared plus 3 squared equals 10 squared. I'll just note it here. There's the 10, there's the x, here's the 3, because we've got a total of 6 as indicated down there, right? Square-based cuboid. So x squared will equal 100 minus 9, and that means that x will be equal to the square root of 91. Let's just calculate that. Square root of 91 is equal to 9.54. So the shortest distance is 9.54 meters. Part III, the total surface area of the 4 triangular sections. So only the 4 triangular sections. So 4 of these triangles, which have all got an area of 1/2 base. Now the entire base of the triangle is 6 centimeters. So it's a total of base. And my height of the triangle is this slant height that I had just found in the previous question of 9.54. So let's multiply this out. 4 times 0.5 times 6 times, and I'm going to use the more accurate rendition of my answer, second negative, in order to access that exact answer. And I get 114.47. If I was to round that to 3 significant figures, I would get approximately 114 meters squared. If we had used, no, it's alright, I'll go on. Part 4, the size of the angle between the slant height of the roof and the plane EFGH. Alright, let's get rid of some of this other stuff in the diagram. Wipe it clean so we can start again. I'm looking for the angle between this triangular face and the square face. The way to do this is to draw a slant height on the triangular face, the sloping one. So you always draw the shortest distance that you can on the that goes up to the very top. And then you'll create the shadow line. If we shone a spotlight from above, this O would go directly down, and this would be the shadow that will be formed by the spotlight. And this forms a right triangle. This is obviously half of the entire width of 6, so that's got a width of 3. We already know what this length is. This one right there. We figured it out was 9.54. And so we're being asked for the angle, which is right there, the angle between our FOG triangle and our square base EFGH. So we should just be able to use SOHCAHTOA then. We've got the adjacent side and we've got the hypotenuse, so let's use the cosine law, cosine ratio, excuse me. So the cosine of the angle I'm trying to find is equal to the adjacent side, 3, divided by the hypotenuse, which is 9.54. And then I'll take the cosine inverse in order to find out the angle. So 3 over 9.54. And I'll take the cosine inverse of this. Cosine inverse of 3 divided by 9.54. 71.7 degrees is the angle. 71.7 degrees. And the height of the tower from the base all the way up to O. So I think they're looking from the entire height. We're looking for this 40 plus whatever this height is. So let's call this height right here h. Let's start by finding h. I can use some SOHCAHTOA again, or I could use Pythagoras because I now know what the other two sides are. I'm going to use SOHCAHTOA, and so I notice that the I know that my let me think for a moment. Oh yeah, I guess I could use the angle measure that I've just got and use SOHCAHTOA, or I could do Pythagoras. You know what, I'm going to do Pythagoras because I just did SOHCAHTOA, didn't I? And so the height squared plus the 3 squared is equal to the hypotenuse squared. And so that means that the height squared is going to equal the hypotenuse squared, that's 9.54 squared, minus the 3 squared, and that leaves us with 82.0116. Let's of course take the square root of both sides, and we'll end up getting an answer of, so square, oh dear, my calculator has managed to freeze. Okay, I just restarted my calculator, pause the video for a moment, and I'll get the square root of 82.0116 gives me to 3 significant figures, approximately 9.06. 9.06, and of course the unit is meters. And now I have to add on the 40 meters that I had on the cuboid below it, right? All I found so far is this height of 9.06. Let's add on the 40. So 40 plus 9.06. So I add on the 40. And now I round to 3 significant figures. I end up with 49.1 meters is the overall height of the tower. Alright, part B. Find correct to 3 significant figures the height of this parrot's nest from the base of the tower. So let's draw the diagram. It's been told that the parrot's nest is at a point P on the edge BF. So the edge BF, there's a parrot's nest somewhere along the edge, perched somehow on the edge of the building. A person at point A outside the building measures the angle of elevation to point P to be 79 degrees. So someone standing right here was able to see that that angle of elevation was 79 degrees. And so then it asks for what is the height of the nest from the base of the tower. And so really they're looking for that distance right here. I'm going to call it D. So this is clearly a right triangle, isn't it? And so I've got the adjacent, I want the opposite, and I've got the angle, so let's relate these with a tangent ratio. So the tangent of 79 degrees equals D over 6. If I rearrange, 6 times the tangent of 79 degrees will equal the distance, the height of the parrot's nest, 6 times the tangent of 79 gives me, alright, the parrot's nest then is at 30.9 meters above ground. Okay, so there's your answer, 30.9 meters from the base of the tower. 2 problems to go. Number 13 is a quick one. We just need to convert this many liters to milliliters. And so to convert liters to milliliters, we're going from from big to small. That means we have to multiply, right? Big to small, we multiply. And so we need to multiply by 1,000. And so we'll take our number, 0.001673, we'll multiply it by 1,000, And now we've converted our number into liters. Another way of doing this would have been simply to move your decimal point over 3 times. That's the same thing as multiplying by 1,000, isn't it? You get 1.673 liters. Alright, an object with mass m is traveling at a speed v, which has energy 1/2 mv squared. Alright, there's some physics stuff for you, but they've given you the formula. So an energy equals 1/2 mv squared. Let's find the energy of a comet with this mass traveling at that speed. So I think the energy is just a matter of substituting, isn't it? 1/2, our mass is 351,223, and our v, the speed, 176.334. The v is supposed to be squared. So here we go. We've got 1/2, which is 0.5, times 351,223, times 176.334 squared. Gives me a final answer of, gosh, that is big, but it says to 6 significant figures, and so let's write down only the first 6. 5, 4, 6, 0, 4, 0, but the number after the 0 is a 7, which is bigger than 5, so I need to change this digit, the 0, into a 1, and then everything afterwards becomes zeros. That's 4 different zeros that follow. There's 6 significant figures. And I should probably include units. They told me that in this situation, units is joules for energy. Okay, so this is energy equals. Alright, part C says the momentum of an object is given by the mass of the object, so that's kilograms, mass, multiplied by its speed. And we know that speed is in meters per seconds. So what is the correct combination of units? Well, this is like kilograms over 1, isn't it? And so we end up with kilograms, we have kilograms meters divided by seconds, and those would be the units for momentum. And the last question is number 14. Back to some triangles. So we need to start by calculating the length of BD. BD is a member of this top triangle about which we already have 3 pieces of information. We can see it's not a right triangle, and we don't have an opposite pair, so we must use the cosine law. I'll call BD x. Because I'm looking for a side, let's use the first version of the cosine law. 15 squared plus 20 squared minus 2 times 15 times 20 times the cosine of the angle in between. Okay, and then I'm going to take the square root of all of this. See what I get. Square root of 15 squared plus 20 squared minus 2 times 15 times 20 times the cosine of 110 degrees. Uh-oh. I must have typed something in wrong. Peculiar. Let's check what did I do? Go to 15 squared plus 20 squared minus 2 times 15. Oh. Maybe this is what happened. 15 times 20 times the cosine of 110 degrees. Okay. There it is. Okay, I must have made a mistake with the parentheses. So my length of BD then is 28.8 meters. Alright, calculate the size of angle BCD. That's this one down here. Well, down in that bottom triangle, I don't have any evidence to show that it's a right triangle, so I can't use SOHCAHTOA or Pythagoras. And I do have an opposite pair right there, the 22 and the 30 degrees, so I should be able to use the sine rule. Sine of 30 degrees over its opposite partner of 22. And now I'm trying to find angle C, so let's begin by working with its opposite side, which I just solved for in part A. It's 28.8. And so I'm looking for the sine of angle C over its opposite length, which is 28.8 meters. Alright, now I filled in the sine law. Let's cross multiply. So 28.8 times the sine of 30 degrees equals 22 times the sine of C. Let's divide both sides through by 22. And now to get the C alone, I need to bring the sine across to the left-hand side where it becomes a sine inverse of 28.8 times the sine of 30 all over 22. So here we go. Sine inverse of 28.8 sine 30. Close the parentheses because I'm finishing my angle before I start dividing by the denominator of 22. And now that final parentheses is to close my sine inverse function. And I get an angle of 40.9 degrees when I round to approximately 3. When I round to exactly 3 significant figures. Now, one student gave the answer to correct to only one significant figure. So instead of finding an answer of 40.9 degrees, they found their answer to be, I guess, write down the length of BD, correct to one significant figure. Oh, yeah, alright. I had 28.8 meters. Now I need to write down the length of BD correct to one significant figure. That will round to 30 meters. So one significant figure, and anything after that first significant figure must be a 0. Alright, part D. Find the size of angle BCD that the student calculated, giving your answer correct to one decimal place. Oh, I see. So instead of using the 28.8 meter measure, the student who prematurely rounded is using a 30 meter measure instead. So we're really doing the exact same calculation as I just did. Let's call it up. Oops, that's not what I meant. There, I want to call up the entry that I just had, but instead of the 28.8, let's change that to the student's inaccurate value of 30. So they had 30, and let's delete the other stuff. Okay, so we're just replacing the 28.8, the more exact value that we found, with the 30, which we know is the less precise value. And let's see what we get. And we're supposed to give our answer correct to one decimal place, and so for us that's going to be 43.0 degrees to one decimal place. And lastly, let's find the percentage error. Percentage error wants us to take the difference between the estimated and the exact. And our exact, what was our exact angle measure? I've forgotten. 40.9. Okay, so we had 40.9. We'll take the difference and then we'll divide it by the exact angle measure. Ours was the more exact one. And then we'll multiply it by 100%. Basically, you see, we're trying to find out what is the difference between the inaccurate one that the student got by prematurely rounding and the correct answer relative to what the correct answer really was. So how bad was this margin of error relative to the overall size of the angle? And so we got 43 minus 40.9, and we'll take that result and divide it by the exact amount, 40.9, and multiply by 100 to convert it into a percent. And we get 5.13%. So approximately, to three significant figures, we had a 5.13% percent error. And that finishes the review. Good luck studying for the test.